Hello and welcome. Isaac, sorry, Feldmarsh and Ines are here. Good morning. I hope you guys are doing okay. Here we go. Matthias, Isaiah, Cassidy. Okay, who's Shakan or Shakan? Good afternoon. Oh, hey, that's interesting. Are you somewhere else? Okay, all caps Sepchich. Okay, interesting. Okay, let's see. Cassidy is here. All right. Oh, hey, buddy, how's it going? Good to see you. And who's all? It's Liam. Okay, cool. Okay. So we're looking for Lauren. Hi. Good morning. Good morning. And we're still looking for Lillian and Theo. Are they here? Lillian and Theo, are you here? Hey, okay, good. Good. Okay, glad you guys are here. If one of you could pop in the group or send a message to Lillian and or Theo in case they forgot, on WhatsApp, a reminder would be good in case they space that they're supposed to. Good, thank you. And can somebody message Theo, please? Okay, just in case he forgot that we're doing this thing. So I've got good news for you guys. Look what I got. I got new markers. Here we go. 2 sets, so we can do all kinds of colorful stuff on the board today. And yeah, it came with Amazon. Amazon's awesome. Those drivers are working hard. Tip your Amazon drivers generously. They're risking their lives so you can get your stuff. So here we go. Let's get started. We talked last week about circuits, and specifically, we reviewed our ski resort analogy. Okay, and what we did there was we said, well, oh, this is not. Oh, here we go. Maybe the thick end. Oh, yeah, that's smooth. That's nice, right? That's really nice. So we said let's take just a very straightforward. I don't know if I like this. I'm gonna use I've got 2 kinds. I think I like the round point better. Let me see. The round point is maybe better. There we go. There we go. We took this kind of simple circuit. It's literally simple. There we go. Like that. And we said, okay, we've got a voltage difference over here. We've got a resistor over there. We've got a current flowing. Okay. And we can also put in meters that measure the voltages. Like we said, for example, we'd like to think about this. Hang on, we'll get there in just a second. We'd like to think about this like a ski resort analogy. So the analogy we used was a slope like that, okay, where you can ski down. That works, okay? So you can kind of ski down this thing, and the slope is kind of like the resistor. And over here, you have a ski lift. Okay, where the skiers are being lifted to the top, and then they can ski down, and the skiers are effectively kind of like the current. So the current is the skiers per time. Okay, the delta V, well, That is the height difference from side to side. We said, okay, let's imagine we had a giant with a ruler measuring that. That's kind of like a voltmeter. The voltmeter measures the height difference. That works. Delta V is the height difference. Okay, all good. Those are the big ones. And then, of course, the resistance is the slope there. Good. This is delta V here. There we go. And these are the skiers, or the current. We also said that we could measure the current by putting an ammeter in here. And the ammeter, for you guys to remember, was some kind of turnstile. Let's do it like a turnstile. Well, that's very small. A turnstile or an electronic registering system that measures how many people come through here, and just to get that data. Over here, we could do the same thing, and we said this is important. We could put this ammeter in down here, like we did in that picture, but we could also put it in somewhere else, like at the top. If we had a second turnstile at the top, A2, it would measure the same thing. So we can have the people go through a stupid turnstile again over here. I'm not sure if this symbol makes any sense. Kind of a thing you turn through that would work, and counts them again. And of course, the same amount of skiers that come into the ski lift exit the ski lift. In the same way over here, the amount of charges that enter the power source also exit the power source. Okay, and the same thing applies also for voltage. If we had a voltmeter over here, like we have our crazy giant over there, we could also remeasure the voltage over there. And we could be like, hello. Of course, the distance the ski lift lifts you up to the top is also the distance that you ski down vertically on the ski slope. Those have to be the same, obviously. Okay, those are the same, and the currents are the same. Now we're going to take that idea and we're going to expand it, and we're going to use the same idea to analyze more complicated circuits, because it's really powerful. Those two ideas are really powerful ideas. The ideas that these charges are, of course, conserved. Whatever charges make it into the power source exit the power source. The skiers that go into the ski lift exit the ski lift. And the other idea that the height, of course, the height up equals the height down. Those are important concepts, and we'll actually call them rules. Okay, and to understand them, we're going to do a simple circuit that's a little less simple than what we just had. So this is just one item. Now we're going to do a circuit that has two. Okay, so we're going to go again with a power source. And this time we're going to go over here and take one resistor and put a second resistor behind it. Okay, so we have here R1 and here R2, and we still have over here some kind of power source that's lifting the charges up. Okay, and then of course there's still current flowing here because they're skiers. Now, let me ask you a question. This is our simple circuit as we think about how this works. We want to have an analogy, and of course we're going to have a ski resort analogy, and you guys might have actually faced a situation like that when you went skiing. Unfortunately, only for a few days, only for a week, but at least you got to go. And the question I have for you is, when your skiers ski through your resistor R1, when they've skied down resistor R1, here's the bottom. Okay. So we've lifted you up to the top. Okay, here's delta V. We've lifted you all the way through to the top, with the power source, and now you're skiing down. Once you've skied through R1, are you at the bottom or not yet? Bottom, B, or not yet? N. Everybody answer. Are you at the bottom or not yet after skiing through R1? Good. So just to thank you, Nessa. Nessa said you're not yet. Good, 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 good. Excellent. So you're not yet at the bottom. Good. And now the question is correct. You're not yet at the bottom. Well, how about if you ski through R1 and R2, right? Then are you at the bottom or not yet? Now you're skiing through R1 and then you're skiing through R2. Are you now at the bottom, B, or not yet, N? Ooh, interesting. Okay. Wait. Yes, you are. Bottom. Okay, yes. Okay, we do get all the way to the bottom. That's correct. We all get to the bottom after R1 and R2 because if you look at the circuit over here, after you go through R1 and R2, you're now back at the bottom of the ski lift. So let's draw that in like this. We're going to draw it in like this. You've got R1. And then we have a little horizontal section. That's the next one. So here's R1. And here's R2. Okay. That looks pretty. Didn't know electrons were the flash. Okay, good. So now, here are a few questions about the situation. Now, first question. Our ski lift lifted us up a certain distance. Okay? Okay. And that distance, the distance we lifted up, we also call the potential difference, or delta V. Delta V is the potential difference. Now, when we ski down R1, we ski down a certain amount of that potential difference. When we ski down R2, we also ski down a certain amount of potential difference. Tell me about let's call this V1, delta V1, and let's call this V2. So let's say delta V over here as an example. Ooh, colors. We've got all these beautiful colors. Let's do an example in red. Let's say this delta V overall, okay, is 12 volts. And let's say delta V1, the one that's being measured here, is equal to 3 volts. 3 volts. Could you guys tell me how big delta V2 should be in that case? If overall the delta V is 12 volts, the distance lifted up by the ski lift, and you come through the first resistor, you go down 3 volts. How much do you go down through the second? 9 volts. Good. 9 volts. Good. Good. Yep. So we went up 12, then we go down 3. Then in order to get to the bottom, we have to go down another 9 to get back to the bottom. Okay, you guys following that? Okay, everybody's got that. Now, we're going to, that's right. Good job. What you're doing there, and this makes sense over here, of course, as well. If the ski lift lifted you up 1,200 meters to the top, Höhenmeter, as they would say in German. And then you go down the first slope, and the first slope has a height difference of 300 meters. And of course, the second slope has to have a height difference of 900 meters in order for you to get back to the same place you started from. What you're doing there is you're applying a rule that's really, really important in circuit analysis, and it's called Kirchhoff's loop rule. Is that still showing up? It is. Kirchhoff's loop rule. So we sometimes abbreviate this KLR. KLR. Good. And we have just enough room here to write it down. And we're going to write it down like this. That the total potential difference in a loop is equal to 0 volts. Now let me explain that to you in a little bit of a detail, how we just used that. So what I mean by a loop is that you choose a point in your circuit where you start. So for example, let's choose orange. Here we go. So we've chosen this point as our starting point. Okay? We've chosen this as our starting point for a loop, and we're going to go through a loop in this direction until we come back to the same spot. By definition, that's what a loop is. That's not really super bright showing up. I want more color to show up better. Okay. I got excited about these markers. I'm not sure how good they are. Okay. So we're going to go through this loop. In this case, in the clockwise direction. We could have gone either way. Hi, Lillian. You can always watch the rest later, okay? So there we go. We could go the other direction, doesn't really matter. And what the loop rule is saying, that if we add up the voltage differences through a loop, then they have to add up to 0. What does that mean? So here we go. We're going through a ski lift. The ski lift lifts us up. We said delta V is 12 volts, but delta, of course, always is like, well, which one's bigger, which one's smaller? Well, we're going from the bottom of the ski lift to the top of the ski lift. So this power source gives us plus 12 volts. That's the example here. We're going to apply the example here. And I know we're a little bit low there, so I'm going to go over that. And that orange is just not showing up. I'm going to not use it. Let's try purple. Okay. There we go. That's better. That's showing up better. So let's take a look here. So we have plus 12 volts is our first step. Okay. Our first step is plus 12 volts because the power source, ski lift, is lifting us up 12 volts. Now the second step is we come down through our first resistor. How do we know where we're coming down? We're coming down because we're going in the direction of the current. And the current flows naturally downhill, right? Okay, so the current flowing through here is associated with a voltage drop, of course. And I gave you that voltage drop. It was 3 volts. So we drop 3 volts in that first resistor, minus 3 volts. And then we drop another amount in the second resistor, delta V2. The voltage drop in the second resistor. And according to Kirchhoff, this whole sum is equal to 0 volts. So 12 minus 3 minus X, or minus delta V2, is 0. So you guys quickly figured out that, of course, delta V2 is going to be equal to 9 volts. This seems trivial, and that's why the other physicists, when Kirchhoff came up with this stuff, denied him the name law. So I'll get to that question in a second. So they just told him, okay, you can have something too. We'll give you a rule. We got Ohm's law, we got Ampere's law, and we got Kirchhoff's rules. Okay, now here's a good question regarding how many volts are left. So you're right, there is no more volts left. Okay, so remember, in order, that's Isaac. No, that's Liam. Liam, all Kapsepchich. Okay, so when we measure a voltage, we're always measuring a voltage difference between 2 points. So the question of how many volts are left at this point is nonsensical. We can't even ask that question because the voltage difference, the potential difference, is always from top to bottom, from here to here, that kind of thing. So you have to ask a difference between two positions because it's like measuring a height difference. You can't say, what's the difference in the position at a point? Because at that point to itself, of course, it's zero, but that's true of any point. Okay, so when you say there's no voltage left at this point or no volts left, well, we're at the bottom. We have to be lifted up again in order to go down the slope. Okay, I don't know what that means, Liam. Do you mean like the bottom resistor R2? Because it does have a voltage difference of 9 volts across the bottom. So the top had 3, the bottom has 9 volts. Then when you're through there, then you've dropped all 12 volts that you were pushed up, and you drop down 3, down 9 more, and now you're at the bottom. In terms of how this works for a actual ski resort, good, exactly. I totally agree. And I think you're having trouble, and this is a very common mistake. So don't feel bad if you're having trouble wrapping your head around this. We always think is how many volts do we have? Well, we don't have volts at a point. We always have volts between 2 points. Okay, so you have to always compare this position to this position. So if we look at our circuit, between these 2 points, there's 12 volts. Between these 2 points, there are 3 volts. Between these 2 points, there's 9 volts. At a point, there is no specific voltage. So good, throwing more stuff out there, Liam. Excellent. Recharged is a dangerous word, okay? And I mean, it's dangerous because it has in it the word charge, okay? And I just want to briefly talk about that. It's okay you said it because this is the very common misconception about this process. Because, and we'll come back to the voltage in just a second and the potential difference, but let's talk about the current for just a second. So we said, okay, we got 12 volts, 3 volts, 9 volts, adds up correctly. Let's talk about the current. Okay, and let's say I told you that the current that starts up here is 2 amperes. I'm just telling you that. Okay, so I equals 2 amperes. Shows up, shows up. Now, let me ask you this. How much current comes out at the end? This is the start, and this is the end. How much current comes out at the end? Two amperes is good. Okay, 2 amperes is correct. So, and of course that makes sense because the amount of skiers that were dropped off at the top is the same amount of skiers that came through this. It's the same amount of skiers that came through there. Something happened in the video? Lauren? Oh, okay. Good. So 2 amperes flow through here, flow through here. So the same amount of charge flows through each part. So what happens to the amount of charge in the circuit? Do the resistors consume charge? Is charge consumed by the resistors? Yes or no? Okay. No. Oh, good. Yes, no. Yes, no. Okay. Charge consumed? Question mark. That was the question I asked. Good. And I'm glad. That's okay. No worries. I'm asking the question because this is a common misconception. Because we even use words like "I've got to charge my phone." Oh, I've got to recharge. I'm a charger. It's a charger. Okay, Isaiah. Good. So the charges are not consumed in a circuit like this. Of course not, because the charges move through the circuit and they get energy and they spend energy on the way down. They do not get consumed themselves. The charges move on. Okay? So that's an important, really important concept that we have here. Now, taking a look here, we know now there are 2 amperes flowing through the circuit. There are 3 volts here, and they flow through there. And then the 2 amperes flow through this 3-volt resistance, and then the 2 amperes flow, okay, the 2 amperes drop 3 volts here, and then they drop 9 volts here. We didn't say how much resistance those 2 resistors have, but we can use Ohm's law to actually figure it out. I'm going to scooch down a little bit to use the space down here. Okay, so taking a look, remember resistance. Well, what is resistance? Resistance is a measure that for that, how much voltage is required to push a certain amount of current through a circuit. That's what Ohm's law is. This is a little crooked. Sorry about that. Delta V. Make the delta bigger. So that's Ohm's law. Ohm's law says how many volts are required to push some current through a resistor. So for our first one, R1, well, let's figure that one out. Okay, R1, how many volts drop across the 3 resistor? First resistor. Yeah, Isaac, that's the same thing, but I'm just using delta V instead of V. But yeah, you're fine. So the resistance of the first resistor is how much voltage drop there is across the first resistor divided by the current there. Okay, so delta V1 is 3, is correct? And the current is 2 amperes. So we have 1.5 ohms. 3/2. Good, Isaac. Okay. Everybody else with us? To find that resistance, so this is the general equation. This is Ohm's law. Yep, you're with me? 3/2? Okay, so the resistance of the first resistor is 1.5 ohms. We just found that out. Well, let's take a look at the second one, and you guys work that one out. How big is R2? Okay, how big is R2 in this situation? How much resistance is that? Correct. Liam, correct. Potential difference delta V divided by current is correct. Okay, R2, you guys figure it out. How much is the resistance R2? Good. Yes. Very nice. So You guys are doing it right. The voltage drop is 9 volts. We still have 2 amperes going through here, and this is 4.5 ohms. Okay? Well, here comes the last one, and then we're going to be done. How about the total resistance? Okay, the total resistance is how much resistance R1 and R2 have together. Now, there's two ways of looking at this, but we should first of all look at it in terms of Ohm's law. Ohm's law says that the total resistance is equal to the total voltage. That's showing up okay, kind of small down there. I'm going to make it a little bigger. Whoopsie. Don't use your fingers for this. It's not a good idea, but oh well. Okay, so R total equals delta V total divided by I total. Showing up? That is showing up. Okay, good, excellent. So let's write that down. We can say, okay, our total equals 12 volts divided by 2 amperes is 6 ohms. We get 6 ohms of resistance in total based on the definition of how resistance is defined. It's how much potential difference is required to push a certain amount of current through a resistor. Well, let's take a look at our results quickly. We have 6 ohms for our total resistance. We have R2 is 4.5 ohms, and we have R1 is 1.5 ohms. Okay? Well, it seems pretty obvious that the total resistance is actually equal to the sum of the individual resistors. And we can make that into a little law. Okay? Here it is. The resistance for a series circuit is just the sum of the individual resistors. Now we stopped at 2, but we could have kept going. And we could come up with R1 plus R2 and so on and so on and so on. If we had 3, 4, 5 different slopes after each other. Okay? And that's our introduction to series circuits and Kirchhoff's loop rule. Okay? And we're at the end of the time. Good job, team, at getting stuff done. Yes, you just add the resistances together. You're getting stuff done. You're turning things in on Classroom. Good work with that. Hang in there. I'm going to put together a little activity for you guys to use with the FET. I think it'll be fun. We have no meeting again. Wait, we do have one more meeting this week. Sorry. And then we'll talk about parallel circuits. So just a reminder, we are meeting on Thursday. Whoa, that's extreme close up. Thursday, 11:45 to 12:15. Thursday, 11:45 to 12:15. And we got some assignments online. Please complete those. And otherwise, we are done. Okay, hang on. Yes, Liam. Yeah. So I'll wait for your question, but I'm gonna answer what I think it is. So you're not okay. That's cool. You can download them, install them, and make them work on your computer, or some of them you can actually run in a web browser, and they're different. So just as long as you get all of them working, I'm okay. And I think there's just one actually for you guys. I'm not sure, but make sure you have the circuit FET working for you, and however you get it to work is cool. Yeah, correct. So they're different. So some work one way, some work another. They've been around for a long time, and they've developed basically these simulations at different times when different technology was basically the best way to go. So some work on Flash, some work on Java, and some work actually as little downloads. Yes, correct. Just make sure you actually get them to work for yourself, specifically the circuit toolbox. Okay. I'm going to hang up on you guys. Nice hanging out, and stay healthy, stay inside, do get some exercise, and be nice to the people around you, and I'll see you on Thursday.